My name's Jake Domingues, and this is my lab 3 for circuits. This is a observation lab with a single experimental model, and I created a circuit, and we measured various different basic models using a multimeter. And the point of this experiment was to just experiment with circuits. So the data from this lab is best viewed through the Ohm's law and law of capacitance. Ohm's law sets a relation for different ohmic circuit elements like resistors, in this case in light bulbs. Voltage differences in current are also used to relate the resistance in the V equals IR equation. Law of capacitance tells us how much charge a capacitor can hold and is also used to calculate that voltage difference. So we have two circuits here. Our first circuit was just with a battery, a multimeter, two resistors of differing resistance, and another multimeter before going back to the battery. This was all in series. We use the multimeters in different ways to analyze the circuits and its elements, and we'll get into that data in a little bit. Our RC circuit had the same battery, 3 volts, and a capacitor, as well as 2 light bulbs with different resistance, and we used a phone timer to analyze how long the discharge and charge took for our capacitor. So here's our first circuit. You can see the battery on the right hidden behind the body armor bottle, our 2 multimeters, as well as our 2 resistors you can see in the middle of the current, in the middle of the circuit right there. And as you can see, it's all in series. Same with our RC circuit. It's all in series. Our battery on the top, our capacitor on the right, all bulbs on the left. So our big data. Resistor 1 was 47 ohms, and resistor 2 was 100 ohms. We used a voltmeter to calculate this. And then since it's all in series, our batteries, you saw there was 2 batteries in the little holder, but since they're in series, that's 3 volts, because they're both 1.5 volts. So we know that our current at all points has to be our V over R. Our Req was 147 in this case because we just had 2 resistors in series and we can just add them up. Obviously, this wasn't exactly true. There was a slight difference due to the fact that our wires have some resistance and our ammeters and voltmeters that were plugged in also had a resistance, our multimeters. We reversed the pins in the ammeter to check it, and it gave us the same value, but just negative. Because if you think about it with the loop rule and stuff, that it would have to be negative for it to work. Our voltage across R1, we did the math and we checked it with the voltmeter, and they're pretty similar. Was 0.847 volts, and our voltage across R2 was 1.86 volts. Our voltage across the ammeter was 0.01 volts, and we also know that there was some resistance in the wire to get us to that 3 total volts that we have in the circuit. Here's our second circuit. You can see our phone timer at the bottom there. Our first light bulb measured with the voltmeter again was 10 ohms of resistance, and our second light bulb was around 15 ohms of resistance. Our time to fully charge was 60 seconds. Our discharge for light bulb 1 was 43 seconds, and our discharge for light bulb 2 was 48 seconds. So what's actually happening in our circuits? Circuit 1 was just a basic circuit, including multimeters to analyze it. Our current remained the same throughout the circuit because that's how ohmic circuit elements and ohmic circuits go. I mean, the current has to remain the same throughout the circuit, no matter the location or orientation if we're looking at the magnitude. There was also a greater voltage difference across circuit elements with higher resistance, and this is due to Ohm's law. All right, so for our second circuit, our RC circuit, at first all the light bulbs were lit up because the current was freely flowing throughout the circuit. And eventually, as our capacitor began to fully charge, the bulbs began to go out. The charged capacitor doesn't allow electrons to flow through. So it keeps these light bulbs unlit because no current can there flow through because electrons aren't allowed to go past it. When dimmed, this is how we knew the capacitor was fully charged, and that's when we stopped our timer. The lower the resistance on the light bulb, the lower the time constant, and this is backed up by our data here. We figure this out, or we prove this by plugging both of our charged capacitors into just one light bulb and seeing how long it took to discharge before the light bulbs to go out, of course. All right, so what if we took a charged capacitor with no resistor on the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Use an ammeter to measure how long it would take to charge a capacitor when connected directly to the battery, and the ammeter discuss blah blah blah. If I charged a capacitor with no resistor in the circuit, ideally it would charge relatively instantly. There would be a small buffer because it would be as fast as the battery, or as fast as the electrons can move from the battery to the capacitor. So this is heavily dependent on the mobility of our wires. The ammeter and the wire have a small amount of resistance, so that's what actually gave us our little 1 second time, due to the very small resistance in these wires, that didn't allow the electrons to fully flow through as fast as they physically can. And yeah, that's it. Thank you very much.